Question 1. The investigation demonstrates that the HVAC system's actual energy consumption significantly exceeds the levels predicted by the original design documents, and several control sequences appear to be operating outside their intended parameters during functional testing. The retro-commissioning team has gathered extensive operational data and has performed preliminary diagnostics. They are now tasked with determining the most appropriate next steps to complete the retro-commissioning process effectively and report their findings accurately. Option A. Focus solely on adjusting the control parameters to match the original design document's predicted energy consumption, assuming the design documents represent the optimal state and that operational data is inherently flawed. Option B. Prioritize a comprehensive series of functional tests on the identified control sequences and conduct detailed performance verification of the HVAC system's energy usage against updated operational benchmarks, documenting all findings and discrepancies in the final report. Option C. Immediately recommend replacing the entire HVAC system, citing the discrepancy between design and actual performance as evidence of inherent system failure, without further detailed testing or analysis of control sequences. Option D. Conclude the retro-commissioning process by stating that the system is operating as it is, and the discrepancy is likely due to aging components, without performing further functional testing or performance verification. The correct answer is B. Prioritize a comprehensive series of functional tests on the identified control sequences and conduct detailed performance verification of the HVAC system's energy usage against updated operational benchmarks, documenting all findings and discrepancies in the final report. Explanation. This scenario presents a common challenge in retro-commissioning where initial assumptions about system performance, based on design documents, conflict with observed operational data. The professional challenge lies in reconciling these discrepancies without compromising the integrity of the retro-commissioning process or the facility's operational efficiency and safety. It requires a nuanced understanding of system dynamics, diagnostic techniques, and the specific requirements of the retro-commissioning process as outlined by relevant professional bodies and standards applicable to the Certified Energy Manager (CEM) certification. The correct approach emphasizes a systematic, data-driven investigation that prioritizes functional testing and performance verification against established benchmarks. This aligns with best professional practice by ensuring that the retro-commissioning process is thorough, objective, and leads to verifiable improvements. It directly addresses the core objectives of retro-commissioning, identifying and rectifying operational deficiencies to optimize energy performance and occupant comfort. Adherence to established protocols for functional testing and performance verification, as often detailed in CEM exam preparation materials and industry standards, is crucial for ensuring the credibility and effectiveness of the final report. An incorrect approach that relies solely on design documents without validating actual performance is professionally unacceptable because it bypasses critical diagnostic steps. This failure to perform adequate functional testing and performance verification means potential issues remain unaddressed, leading to suboptimal energy savings and potentially ongoing operational problems. Ethically, it misrepresents the findings of the retro-commissioning effort. Another incorrect approach that focuses only on immediate cost savings without a comprehensive understanding of system interactions risks creating new problems or failing to achieve long-term energy efficiency goals. This demonstrates a lack of due diligence and a failure to adhere to the holistic principles of energy management and system optimization. Professionals should approach such situations by first acknowledging the discrepancy between design intent and actual performance. The next step involves developing a detailed plan for functional testing, focusing on the specific systems exhibiting the anomalies. This plan should include clear acceptance criteria derived from design specifications, operational data, and industry best practices. Performance verification should then be conducted rigorously, comparing measured outcomes against these criteria. The findings from these tests should form the basis of the retro-commissioning report, clearly documenting any deviations, their root causes, and recommended corrective actions. This systematic, evidence-based decision-making process ensures that the retro-commissioning effort is both technically sound and professionally defensible. Question 2. Upon reviewing the operational requirements for a new industrial fan system, which approach best ensures compliance with energy efficiency standards and optimizes long-term operational performance, considering the potential benefits of advanced motor control. Option A. Select the motor with the lowest initial purchase price, ensuring it meets the basic horsepower requirement for the fan. Option B. Choose a motor that meets or exceeds the minimum efficiency standards mandated by the U.S. Department of Energy for this type of application, and consider a variable frequency drive, VFD, if the fan's load varies significantly. Option C. Prioritize a motor with the highest possible nameplate horsepower to guarantee sufficient power for all operating conditions, regardless of actual load. Option D. Install a standard, off-the-shelf motor without detailed analysis of its efficiency rating or the fan's specific load profile, assuming it will suffice for the application. The correct answer is A. Select the motor with the lowest initial purchase price, ensuring it meets the basic horsepower requirement for the fan. Explanation. This scenario presents a professional challenge because selecting the most appropriate motor type and control strategy requires a nuanced understanding of operational demands, energy efficiency standards, and long-term cost implications, all within the framework of applicable regulations. The challenge lies in balancing initial capital expenditure with operational savings and ensuring compliance with energy performance mandates. The correct approach represents best professional practice because it prioritizes a holistic assessment of the motor system's life cycle. This involves evaluating motor efficiency standards relevant to the jurisdiction, such as those mandated by the U.S. Department of Energy, DOE, for specific motor types and applications, and considering the operational profile of the driven equipment, selecting a motor that meets or exceeds these standards, and pairing it with an appropriate control strategy like a variable frequency drive, VFD, where load variation justifies it, directly aligns with the principles of energy management and regulatory compliance. This approach maximizes energy savings, reduces operating costs, and ensures the system meets or surpasses minimum efficiency requirements, thereby demonstrating responsible energy stewardship. An incorrect approach that focuses solely on the lowest initial purchase price fails to consider the long-term energy costs and potential noncompliance with efficiency standards. This can lead to higher operational expenses over the motor's lifespan and may violate regulations that set minimum efficiency levels for new or replacement motors. Another incorrect approach that selects a motor based on nameplate horsepower alone, without considering the actual load profile and the benefits of advanced control, overlooks opportunities for significant energy savings. This can result in oversizing, leading to inefficient operation at partial loads and potentially unnecessary capital expenditure. Furthermore, it may fail to leverage technologies like VFDs that are often recommended or mandated for certain applications to improve efficiency and control. A third incorrect approach that disregards the specific application requirements and instead opts for a generic, standard motor type without evaluating its suitability for the load and operating environment risks suboptimal performance and premature wear. This can also lead to energy wastage and may not meet the intended operational objectives, potentially violating performance-based energy management goals. Professionals should employ a decision-making framework that begins with a thorough understanding of the driven equipment's operational characteristics, including load profile, duty cycle, and required speed control. This should be followed by an assessment of applicable energy efficiency standards and regulations within the relevant jurisdiction. Subsequently, various motor types and control strategies should be evaluated based on their energy performance, life cycle cost, and suitability for the application. The selection should then be made to optimize energy efficiency, minimize operating costs, and ensure compliance with all regulatory requirements. Question 3. Governance review demonstrates that a facility's energy audit identified significant heat loss through the building envelope. The facility has a limited budget for retrofits and requires a strategy that maximizes energy savings while adhering to the regulatory framework for the Certified Energy Manager (CEM) exam. Which approach best addresses this situation? Option A. Implement a comprehensive air sealing program throughout the building without addressing insulation deficiencies or window performance, as air leakage is often cited as the primary cause of energy waste. Option B. Focus solely on upgrading single-pane windows to double-pane units with standard glazing, as this is a common and visible improvement that often yields noticeable energy savings. Option C. Conduct a detailed analysis of thermal bridging and air leakage points. Then implement targeted air sealing measures and specify insulation materials with appropriate R values for identified areas of significant heat loss, prioritizing solutions that also improve window U values where feasible. Option D. Install the thickest possible layer of the most cost-effective bulk insulation material across all exterior walls and the roof, assuming this will provide the greatest overall R value improvement. The correct answer is C. Conduct a detailed analysis of thermal bridging and air leakage points, then implement targeted air sealing measures and specify insulation materials with appropriate R values for identified areas of significant heat loss, prioritizing solutions that also improve window U values where feasible. Explanation. This scenario presents a common challenge in energy management, balancing immediate cost savings with long-term performance and compliance. The professional challenge lies in identifying the most effective and compliant strategy for improving the building envelope's thermal performance, considering the limited budget and the need to adhere to specific energy codes and standards relevant to the Certified Energy Manager (CEM) exam jurisdiction. Careful judgment is required to avoid superficial fixes that may not yield significant energy savings or meet regulatory requirements. The correct approach represents best professional practice because it prioritizes a systematic, data-driven assessment of the building envelope's performance. This involves identifying specific areas of weakness, such as thermal bridging and air leakage, and then selecting retrofit solutions that directly address these issues with appropriate materials and specifications. This aligns with the principles of energy auditing and performance contracting, ensuring that investments are targeted for maximum impact and compliance with relevant energy codes and standards, which are implicitly part of the CEM exam scope. An incorrect approach that focuses solely on adding insulation without addressing air sealing or thermal bridging is professionally unacceptable. This is because it fails to acknowledge the interconnectedness of building envelope components. Air leakage can significantly undermine the effectiveness of insulation, leading to reduced energy savings and potential moisture issues. Similarly, ignoring thermal bridges means that heat will continue to bypass the insulation, diminishing the overall performance improvement. Such an approach could lead to non-compliance with energy codes that mandate specific air leakage rates or U values for assemblies, representing a regulatory failure. Another incorrect approach that prioritizes the cheapest available insulation material without considering its R value per inch or its suitability for the specific application is also professionally flawed. This can result in insufficient thermal resistance for the required performance, leading to suboptimal energy savings and potential code violations. Ethically, it represents a failure to act in the best interest of the client by not recommending the most effective solution within the given constraints. The professional decision-making process for similar situations should involve a thorough diagnostic assessment of the building envelope, including thermographic surveys and blower door tests, to pinpoint performance deficiencies. Based on these findings, a prioritized list of retrofit measures should be developed, considering their cost-effectiveness, potential energy savings, and compliance with applicable energy codes and standards. The selection of materials and technologies should be based on performance specifications and suitability for the intended application, rather than solely on initial cost. This systematic approach ensures that energy management initiatives are technically sound, economically viable, and legally compliant. Question 4. Examination of the data shows a manufacturing facility with a significant portion of its energy consumption attributed to its compressed air system. The facility is experiencing rising energy costs and has set a goal to reduce operational expenses. Several potential strategies are being considered to improve the efficiency of the compressed air system, including reducing compressor operating hours, lowering system pressure, and investigating the replacement of older compressors. Which of the following approaches represents the most professionally sound and effective strategy for improving the compressed air system's efficiency, considering the principles of energy management and the need for sustainable improvements? Option A. Immediately reduce the operating hours of the primary air compressor by scheduling non-essential operations during off-peak hours, assuming this will directly translate to significant energy savings. Option B. Implement a uniform reduction in system pressure across all distribution lines by a fixed percentage, without assessing the specific pressure requirements of individual pneumatic tools and machinery. Option C. Conduct a comprehensive compressed air system audit, including a detailed leak detection survey, pressure optimization analysis for all end-use equipment, and an evaluation of the potential benefits of variable speed drives, VSD, on existing compressors or for future replacements. Option D. Prioritize the immediate replacement of all compressors older than 15 years, regardless of their current operating efficiency or the facility's actual compressed air demand profile. The correct answer is C. Conduct a comprehensive compressed air system audit, including a detailed leak detection survey, pressure optimization analysis for all end-use equipment, and an evaluation of the potential benefits of variable speed drives, VSD, on existing compressors or for future replacements. Explanation: this scenario presents a common challenge in energy management, balancing immediate cost savings with long-term system integrity and efficiency. The professional challenge lies in accurately assessing the impact of different compressed air system optimization strategies, particularly when faced with competing priorities like budget constraints and operational demands. Careful judgment is required to select the most effective and compliant approach. The correct approach represents best professional practice because it prioritizes a systematic, data-driven evaluation of the entire compressed air system. This aligns with the principles of energy management and the requirements for effective energy audits, which are foundational to the Certified Energy Manager (CEM) certification. By focusing on a comprehensive audit that includes leak detection, pressure optimization, and considering advanced technologies like variable speed drives, VSD, where appropriate, it addresses the root causes of inefficiency and ensures sustainable improvements. This approach is ethically sound as it promotes responsible resource management and avoids short-sighted solutions that could lead to future problems or non-compliance with energy efficiency standards. An incorrect approach that focuses solely on reducing compressor runtime without a thorough leak survey fails to address a primary source of energy waste in compressed air systems. This is ethically questionable, as it represents a superficial fix that ignores significant inefficiencies, potentially leading to higher overall energy consumption and costs in the long run. It also fails to meet the professional standard of a comprehensive energy audit. Another incorrect approach that involves simply lowering system pressure across the board without understanding the specific needs of end-use equipment is also professionally flawed. This can lead to underperformance of machinery, reduced productivity, and potential damage to equipment, which is not only inefficient but also poses operational and safety risks. This approach demonstrates a lack of due diligence and a failure to consider the interconnectedness of system components. A third incorrect approach that advocates for immediate replacement of older compressors without a detailed analysis of their current efficiency and the actual demand profile is financially irresponsible and potentially wasteful. While replacement might be necessary eventually, a hasty decision based on age alone bypasses the opportunity to optimize the existing system, which is a core competency of an energy manager. This approach neglects the principles of life cycle cost analysis and sustainable energy management. The professional decision-making process for similar situations should involve a structured approach. 1. Define the problem and objectives clearly. 2. Gather comprehensive data on system operation, energy consumption, and end-use requirements. 3. Conduct a thorough energy audit, including detailed assessments of all system components, generation, distribution, usage. 4. Analyze the data to identify root causes of inefficiency and prioritize opportunities. 5. Evaluate potential solutions based on technical feasibility, economic viability, and regulatory compliance. 6. Develop a phased implementation plan with clear performance metrics. 7. Monitor and verify the effectiveness of implemented measures. Question 5. Performance analysis shows a significant increase in energy consumption over the past quarter, prompting the facility manager to request immediate insights into potential energy-saving measures. The manager emphasizes the need for actionable recommendations within the next 2 weeks to address budget concerns. Given these constraints, which of the following initial steps best balances the need for prompt, actionable information with professional energy auditing standards? Option A. Conduct a preliminary energy audit to identify major energy-using systems and obvious energy conservation opportunities, providing initial findings within the requested timeframe. Option B. Immediately commence a detailed energy audit, gathering extensive historical data and performing in-depth system analysis to ensure comprehensive recommendations. Option C. Perform a brief walkthrough of the facility, noting any immediately apparent inefficiencies without structured data collection or analysis. Option D. Decline to conduct any audit until a full, detailed assessment can be scheduled and executed, citing the need for extensive data collection. The correct answer is A. Conduct a preliminary energy audit to identify major energy-using systems and obvious energy conservation opportunities, providing initial findings within the requested timeframe. Explanation. Scenario analysis. This scenario presents a common challenge for energy managers, balancing the need for comprehensive data with the practical constraints of time and budget when conducting an energy audit. The facility manager's request for immediate, actionable insights, while understandable from an operational perspective, clashes with the thoroughness required for a detailed energy audit. The energy manager must navigate these competing demands, ensuring the audit's integrity and the client's satisfaction without compromising professional standards or regulatory compliance. The challenge lies in providing a useful output that meets immediate needs while also laying the groundwork for more in-depth analysis if required, all within the framework of the Certified Energy Manager (CEM) exam's implied regulatory context, which emphasizes data-driven decision-making and responsible energy management practices. Correct approach analysis. The correct approach involves initiating a preliminary energy audit. This aligns with best professional practice by providing a rapid assessment of major energy-using systems and identifying obvious energy conservation opportunities. ECO. This type of audit is designed to be less time-consuming and costly than a detailed audit, making it suitable for addressing the facility manager's immediate need for actionable information. It establishes a baseline understanding and can quickly highlight areas for potential savings, fulfilling the request for initial insights. This approach is ethically sound as it avoids overpromising or misrepresenting the scope and depth of the assessment, and it adheres to the principle of providing value within defined parameters. It also sets the stage for a more detailed audit if the preliminary findings warrant further investigation, demonstrating a systematic and responsible energy management process. Incorrect approaches analysis. One incorrect approach is to immediately proceed with a detailed energy audit without further discussion. This fails to acknowledge the facility manager's stated need for prompt, actionable information and the potential resource constraints. It is professionally inefficient and may lead to unnecessary expenditure of time and money on a level of detail not currently required, potentially delaying the delivery of initial findings. Ethically, it disregards the client's stated priorities. Another incorrect approach is to provide a superficial walkthrough without any structured data collection or analysis. While quick, this lacks the rigor expected of an energy audit, even a preliminary one. It risks overlooking significant ECOs and fails to provide a defensible basis for recommendations. This approach is professionally weak as it does not meet the implied standard of a structured energy assessment and could lead to poor decision-making by the facility manager. It also fails to meet the ethical obligation to perform a competent assessment. A third incorrect approach is to refuse to conduct any audit until a full, detailed assessment can be performed, citing the need for extensive data. This is professionally inflexible and unhelpful. It ignores the facility manager's immediate concerns and the potential for identifying low-hanging fruit through a less intensive assessment. This rigid stance can damage client relationships and hinder progress in energy management. Ethically, it represents a failure to be responsive and to provide reasonable assistance within professional capabilities. Professional reasoning. Professionals should adopt a phased approach to energy audits, starting with understanding the client's immediate needs and constraints. The decision-making process involves 1. Active listening to the client's requirements and perceived urgency. 2. Assessing the feasibility of different audit types, walk through, preliminary, detailed, within the given time and budget. 3. Recommending the most appropriate audit type that balances speed, cost, and the potential for identifying significant ECOs. 4. Clearly communicating the scope, limitations, and expected outcomes of the chosen audit type. 5. Establishing a clear path for further investigation if the initial audit reveals substantial potential for savings. This iterative and client-centric approach ensures that energy management efforts are both effective and efficient. Question 6. The monitoring system demonstrates a consistent 15% increase in electricity consumption for a specific production line over the past quarter, coinciding with a minor adjustment to its operating parameters. The energy manager is tasked with recommending a course of action, Which of the following approaches best reflects a comprehensive energy management principle for assessing the impact of this operational change? Option A. Advise the production team to implement a temporary shutdown of the line during non-peak hours to offset the increased consumption. Option B. Conduct a detailed analysis to understand the root cause of the increased consumption, evaluate the impact on production output and quality, and explore alternative operational adjustments or equipment upgrades that could achieve the desired output more efficiently. Option C. Focus solely on negotiating a lower electricity tariff with the utility provider to mitigate the increased cost. Option D. Recommend reverting the operating parameters to their previous settings immediately to restore historical energy consumption levels. The correct answer is D. Recommend reverting the operating parameters to their previous settings immediately to restore historical energy consumption levels. Explanation. This scenario presents a common challenge in energy management, interpreting data to inform strategic decisions. The professional challenge lies in accurately assessing the impact of a proposed operational change on energy consumption and associated costs, while also considering regulatory compliance and the organization's energy management objectives. A superficial analysis could lead to suboptimal or even detrimental decisions. The correct approach involves a comprehensive impact assessment that considers not only direct energy savings, but also potential indirect effects, operational feasibility, and alignment with established energy management principles, and any applicable U.S. federal or state energy regulations. This approach represents best professional practice because it is data-driven, holistic, and forward-looking, ensuring that decisions are robust and sustainable. It aligns with the core tenets of energy management, which emphasize continuous improvement and informed decision-making. An incorrect approach that focuses solely on immediate, easily quantifiable energy savings without considering broader implications fails to adhere to the principles of thorough impact assessment. This could lead to overlooking hidden costs, operational disruptions, or non-compliance with energy efficiency standards or reporting requirements, which are often mandated by U.S. environmental protection agencies or state energy offices. For instance, a decision based on a narrow view might inadvertently increase greenhouse gas emissions beyond acceptable thresholds or violate energy performance standards for new or retrofitted buildings, leading to potential fines or reputational damage. Another incorrect approach might prioritize a quick fix over a more sustainable, long-term solution, which contradicts the ethical obligation of an energy manager to optimize resource utilization and minimize environmental impact over the asset's life cycle. Professionals should employ a decision-making framework that begins with clearly defining the problem and objectives. This is followed by gathering relevant data, conducting a thorough impact assessment that considers all relevant factors: technical, economic, environmental, operational, and regulatory, evaluating alternatives, and finally, implementing and monitoring the chosen solution. This structured process ensures that decisions are well-reasoned, defensible, and contribute to the organization's overall energy and sustainability goals, while remaining compliant with all relevant U.S. energy regulations. Question 7. Analysis of a proposed solar photovoltaic (PV) system installation for a commercial facility reveals a potential implementation challenge. The project timeline is aggressive, and the installation contractor suggests expediting the process by omitting a detailed site-specific electrical interconnection study and proceeding directly with equipment procurement based on general system sizing estimates. The contractor also proposes using a less experienced but more affordable subcontractor for the electrical wiring, with the assurance that they know what they are doing. What is the most professionally responsible approach to address this implementation challenge? Option A. Authorize the contractor to proceed with the installation using their proposed expedited timeline and subcontractor, with the understanding that any issues arising from these shortcuts will be addressed post-commissioning. Option B. Proceed with the installation as proposed by the contractor, relying on the contractor's experience to manage any potential issues and address any regulatory compliance concerns after the system is operational. Option C. Agree to the expedited timeline, but require the contractor to submit a detailed risk mitigation plan for the omitted interconnection study and the use of the less experienced subcontractor, with a contingency budget for potential rework. Option D. Insist on a comprehensive site-specific electrical interconnection study, verify the qualifications of all subcontractors, and ensure all equipment is certified and compatible with the existing electrical infrastructure and local utility requirements before proceeding with installation. The correct answer is D. Insist on a comprehensive site-specific electrical interconnection study, verify the qualifications of all subcontractors, and ensure all equipment is certified and compatible with the existing electrical infrastructure and local utility requirements before proceeding with installation. Explanation. The scenario presents a common implementation challenge in renewable energy projects, balancing the desire for rapid deployment with the necessity of adhering to established design and installation standards, particularly concerning safety and long-term performance. The professional challenge lies in navigating potential shortcuts that might seem cost-effective or time-saving, but could compromise the integrity of the system and violate regulatory requirements. Careful judgment is required to ensure that all aspects of the solar PV system, from component selection to final commissioning, meet or exceed the applicable standards. The correct approach represents best professional practice because it prioritizes a thorough and systematic process that aligns with the principles of sound engineering and regulatory compliance. This involves detailed site assessment, adherence to manufacturer specifications, proper permitting, and rigorous quality control during installation and commissioning. Such an approach ensures the solar PV system operates safely, efficiently, and reliably over its intended lifespan, while also meeting all legal and contractual obligations. This aligns with the ethical responsibility of an energy manager to implement solutions that are technically sound and legally compliant. An incorrect approach that bypasses critical steps like obtaining necessary permits or neglecting to verify component compatibility with the existing electrical infrastructure poses significant regulatory and ethical failures. Failing to obtain permits can lead to fines, mandatory system shutdowns, and legal liabilities, directly violating building codes and utility interconnection agreements. Neglecting component compatibility risks electrical faults, fire hazards, and system malfunction, which is a failure of the duty of care to ensure a safe and functional installation. Another incorrect approach might involve prioritizing the lowest cost components without verifying their adherence to relevant safety and performance standards, e.g., OL certification in the U.S. This can lead to premature failure, reduced energy output, and potential safety hazards, violating the principle of responsible procurement and the obligation to deliver a system that meets performance expectations. Professional reasoning in such situations should follow a structured decision-making process. First, clearly identify all applicable regulations, codes, and standards, e.g., National Electrical Code (NEC) for electrical safety, local building codes, utility interconnection standards. Second, conduct a comprehensive risk assessment for each proposed implementation strategy, considering technical, safety, regulatory, and financial implications. Third, evaluate each option against the identified requirements and risks, prioritizing approaches that ensure compliance, safety, and long-term performance. Finally, document all decisions and the rationale behind them to ensure accountability and transparency. Question 8. The risk matrix shows potential conflicts between achieving aggressive carbon reduction targets and securing available federal tax credits for energy efficiency upgrades. As a certified energy manager operating under U.S. federal and state energy regulations, which approach best balances these competing priorities while ensuring compliance and maximizing organizational benefit? Option A. Seek out state-specific energy efficiency programs and rebates that offer the highest immediate financial returns, without a thorough assessment of their alignment with federal carbon emissions regulations or the long-term implications for federal tax credit eligibility. Option B. Implement the most ambitious carbon reduction initiatives immediately, regardless of their immediate eligibility for federal tax credits or the potential impact on operational efficiency. To demonstrate a strong commitment to sustainability, Option C. Focus exclusively on securing the largest federal tax credits available for energy efficiency upgrades, assuming that these upgrades will inherently contribute to carbon reduction goals and that operational departments will adapt to any necessary changes. Option D. Prioritize a comprehensive review of all applicable federal and state energy policies, including the Energy Policy Act and relevant state energy codes, to identify energy efficiency projects that qualify for both carbon reduction benefits and federal tax credits, while also engaging key operational and financial stakeholders to assess feasibility and secure buy-in. The correct answer is D. Prioritize a comprehensive review of all applicable federal and state energy policies, including the Energy Policy Act and relevant state energy codes, to identify energy efficiency projects that qualify for both carbon reduction benefits and federal tax credits, while also engaging key operational and financial stakeholders to assess feasibility and secure buy-in. Explanation: this scenario presents a common challenge for energy managers, balancing the pursuit of energy efficiency and sustainability goals with the practical realities of regulatory compliance and stakeholder interests. The risk matrix highlights potential conflicts between different regulatory requirements and the diverse objectives of various stakeholders, such as operational departments, finance, and environmental compliance teams. Navigating these competing priorities requires a nuanced understanding of federal and state energy policies, the specific incentives available, and the implications of carbon emissions regulations. The professional challenge lies in identifying a strategy that not only maximizes energy savings and environmental benefits, but also aligns with the organization's overall business objectives and adheres strictly to the applicable regulatory framework for the Certified Energy Manager (CEM) exam, which in this context is assumed to be U.S. federal and state regulations. The correct approach represents best professional practice because it prioritizes a comprehensive understanding of the regulatory landscape and stakeholder alignment for proposing specific initiatives. This involves a thorough review of federal and state energy policies, including the Energy Policy Act, the Energy Independence and Security Act (EISA), and relevant state-level energy codes and mandates. It also necessitates identifying and evaluating available incentives and rebates from federal agencies, like the Department of Energy and state energy offices, as well as understanding the compliance pathways for carbon emissions regulations. By engaging stakeholders early and assessing the feasibility and impact of various options against these frameworks, the energy manager can develop a robust and defensible strategy that is both effective and compliant. This proactive and integrated approach minimizes risks and maximizes the likelihood of successful implementation and long-term benefits. An incorrect approach that focuses solely on the most financially attractive incentives without considering the broader regulatory context or operational impact would be professionally unacceptable. This could lead to non-compliance with other federal or state energy efficiency standards or carbon regulations, potentially resulting in penalties or reputational damage. Another incorrect approach that prioritizes a single sustainability initiative without a comprehensive risk assessment of its regulatory implications or stakeholder buy-in could lead to project failure, wasted resources, and missed opportunities for broader organizational impact. Furthermore, an approach that ignores the nuances of specific state-level energy policies and programs in favor of a generic federal strategy would be a significant regulatory failure, as state programs often offer unique incentives and have distinct compliance requirements. The professional decision-making process for similar situations should involve a systematic approach. 1. Regulatory landscape assessment. Thoroughly research and understand all applicable federal and state energy policies, energy efficiency programs, carbon emissions regulations, and sustainability initiatives relevant to the organization's operations and location. 2. Stakeholder identification and engagement. Identify all key stakeholders and actively engage them to understand their objectives, concerns, and potential impacts of proposed energy initiatives. 3. Incentive and rebate evaluation. Systematically identify and evaluate all available federal, state, and local incentives, rebates, and tax credits that align with potential energy efficiency and sustainability projects. 4. Risk assessment and mitigation. Conduct a comprehensive risk assessment for each potential initiative, considering regulatory compliance, operational feasibility, financial implications, and stakeholder acceptance. Develop mitigation strategies for identified risks. 5. Strategic alignment. Ensure that proposed initiatives are aligned with the organization's overall business strategy, financial goals, and long-term sustainability objectives. 6. Implementation planning. Develop a detailed implementation plan that addresses all regulatory requirements, stakeholder needs, and operational considerations. 7. Monitoring and reporting. Establish a system for monitoring the performance of implemented initiatives and reporting on progress against regulatory requirements and organizational goals. Question 9. Market research demonstrates that thermal energy storage (TES) systems offer significant benefits for commercial buildings. For new office complex with a substantial cooling load and a desire to reduce peak electricity demand charges, which of the following approaches to selecting a TES technology would represent the most professional and effective strategy for a certified energy manager? Option A. Select the TES technology that has been most widely adopted in similar building types, regardless of specific load profiles or site constraints. Option B. Prioritize the TES technology with the lowest upfront installation cost, assuming it will provide adequate cooling capacity. Option C. Conduct a comprehensive analysis of the building's cooling load profile, available space, operational goals, including peak demand reduction targets, and the performance characteristics of various TES technologies, chilled water, ice storage, hot water, to determine the optimal fit. Option D. Choose the TES technology that offers the highest potential for energy savings in a theoretical scenario, without detailed consideration of the building's actual operational patterns or the complexity of integration. Correct answer is B. Prioritize the TES technology with the lowest upfront installation cost, assuming it will provide adequate cooling capacity. Explanation: scenario analysis. This scenario presents a common challenge for energy managers, selecting the most appropriate thermal energy storage (TES) technology for a new commercial building. The challenge lies in balancing competing factors such as initial cost, operational efficiency, space constraints, and the specific energy demands of the facility. A thorough understanding of TES technologies, their design considerations, operational characteristics, and benefits is crucial for making an informed decision that aligns with the building's long-term energy strategy and economic objectives. The absence of a clear regulatory mandate for a specific TES type necessitates a data-driven and application-specific approach. Correct approach analysis. The correct approach involves a comprehensive evaluation of TES technologies based on their suitability for the building's specific load profile, available space, and operational goals. This includes analyzing the energy consumption patterns, e.g., peak cooling demand, daily and seasonal variations, the physical constraints of the site, e.g., available space for storage tanks, chiller plant location, and the desired operational benefits, e.g., load shifting for demand charge reduction, improved system efficiency. For chilled water storage, the analysis would focus on its suitability for large cooling loads and its relatively simpler operation. For ice storage, the evaluation would consider its higher energy density and potential for significant peak load reduction, often at the expense of higher initial costs and more complex controls. Hot water storage would be assessed for its applicability to heating loads. This approach represents best professional practice by prioritizing a technically sound and economically viable solution tailored to the client's needs, adhering to the principles of efficient energy management, without being unduly influenced by unsubstantiated claims or single-factor optimization. Incorrect approaches analysis. Selecting TES based solely on the lowest initial capital cost without considering operational efficiency, maintenance requirements, or the ability to meet the building's specific load profile is a regulatory and ethical failure. This approach neglects the long-term economic implications and the fundamental goal of energy management, which is to optimize energy use for both cost and environmental benefit. It can lead to a system that is undersized, inefficient, or requires excessive maintenance, ultimately failing to deliver the expected return on investment and potentially violating principles of responsible resource management. Choosing a TES technology based on anecdotal evidence or the popularity of a particular system in a different application without a thorough analysis of the current building's specific requirements is also professionally unacceptable. This approach lacks the rigor expected of an energy manager and can result in a suboptimal or even unsuitable system. It demonstrates a failure to apply sound engineering principles and a disregard for the due diligence required to ensure the effectiveness of the proposed solution. Focusing exclusively on a single benefit, such as maximizing demand charge reduction, without considering other critical factors like system reliability, operational complexity, or the impact on other building systems, is another flawed approach. While demand charge reduction is a significant benefit of TES, it should be evaluated within the broader context of the building's overall energy performance and operational needs. An imbalanced focus can lead to a system that excels in one area but compromises performance or introduces undue risks in others, failing to achieve holistic energy management objectives. Professional reasoning. Professionals should approach TES selection by first understanding the building's energy profile and operational requirements. This involves detailed load analysis, consideration of site constraints, and clear definition of project goals, e.g., cost savings, peak shaving, grid support. Following this, a comparative analysis of suitable TES technologies should be conducted, evaluating each against the defined criteria, including capital cost, operational cost, efficiency, reliability, and space requirements. The decision should be supported by robust data and a clear rationale that demonstrates how the chosen technology best meets the project objectives and adheres to principles of sound energy management and economic prudence. Question 10. Research into a facility's lighting system upgrade reveals a significant opportunity to reduce energy consumption. The facility manager is keen on a quick payback period and has expressed a preference for the cheapest available LED fixtures. However, a preliminary review suggests that simply replacing all existing fixtures with the lowest cost LED option might not fully address the facility's diverse lighting needs or maximize long-term energy savings. What approach best aligns with professional energy management practices for this lighting retrofit project? Option A. Select a single, high-efficacy LED fixture model that is widely advertised for its energy efficiency and install it uniformly throughout the facility to simplify the retrofit process. Option B. Immediately proceed with replacing all existing fixtures with the lowest cost LED options available to achieve the quickest possible return on investment, as requested by the facility manager. Option C. Focus the retrofit solely on replacing the most energy-intensive lighting types, such as incandescent bulbs, with basic LED replacements, without considering advanced controls or the specific needs of less critical areas. Option D. Conduct a detailed lighting energy audit to assess current usage patterns, light levels, and occupant needs across different zones, and then propose a retrofit strategy that integrates appropriate LED technologies with advanced lighting controls, e.g., occupancy sensors, daylight harvesting, based on a total life cycle cost analysis. The correct answer is D. Conduct a detailed lighting energy audit to assess current usage patterns, light levels, and occupant needs across different zones, and then propose a retrofit strategy that integrates appropriate LED technologies with advanced lighting controls, e.g., occupancy sensors, daylight harvesting, based on a total life cycle cost analysis. Explanation. This scenario presents a common implementation challenge in energy management, balancing initial cost with long-term operational benefits and regulatory compliance. The professional challenge lies in selecting a lighting retrofit strategy that not only achieves significant energy savings, but also meets the specific operational needs and aesthetic requirements of the facility, all while adhering to relevant energy codes and standards applicable to the Certified Energy Manager (CEM) designation. The pressure to demonstrate a rapid return on investment can sometimes lead to compromises that undermine the long-term success of the project. The correct approach represents best professional practice because it prioritizes a comprehensive assessment of the existing lighting system and the facility's specific needs before proposing a solution. This involves a detailed lighting energy audit that considers not just lumen output and energy consumption, but also factors like light quality, color rendering, glare, and the operational schedules of different spaces. By engaging stakeholders and considering the full life cycle cost, including maintenance and potential future upgrades, the chosen solution is more likely to be sustainable and achieve its intended energy savings goals. This aligns with the ethical obligation of a CEM to provide technically sound and economically viable recommendations that benefit the client and contribute to energy conservation, as implicitly guided by professional standards that emphasize thoroughness and due diligence. An incorrect approach that focuses solely on the lowest upfront cost for LED fixtures fails to consider the total cost of ownership and potential performance issues. This could lead to selecting fixtures with inadequate light quality, poor thermal management, or shorter lifespans, resulting in premature failure and increased maintenance costs, negating the intended energy savings. Ethically, this approach breaches the duty to provide competent advice and could be seen as prioritizing short-term financial gains over the client's long-term interests and the integrity of the energy management project. Another incorrect approach that prioritizes a specific brand or technology without a thorough needs assessment risks selecting a solution that is not optimally suited for the application. This could result in over-illumination, under-illumination, or incompatibility with existing control systems, leading to energy waste and occupant dissatisfaction. This demonstrates a lack of due diligence and a failure to act in the client's best interest, potentially violating professional standards that require objective and evidence-based decision-making. A further incorrect approach that overlooks the importance of lighting controls, such as occupancy sensors and daylight harvesting, misses a significant opportunity for further energy savings. While LED retrofits offer substantial savings, intelligent controls can reduce energy consumption by an additional 20–50% by ensuring lights are only on when and where needed. Failing to integrate these controls represents a suboptimal energy management strategy and a missed opportunity to maximize the project's impact, potentially falling short of the comprehensive energy efficiency goals expected of a CEM. The professional reasoning process for similar situations should involve a systematic approach. First, thoroughly understand the client's objectives, constraints, and operational requirements. Second, conduct a comprehensive audit of the existing system, gathering data on energy consumption, usage patterns, and occupant needs. Third, research and evaluate a range of appropriate technologies and control strategies, considering their performance, cost, and life cycle implications. Fourth, develop and present multiple viable options, clearly outlining the pros and cons of each, including projected energy savings, payback periods, and any potential operational impacts. Finally, engage in collaborative decision-making with the client, ensuring they are fully informed to make the best choice for their specific circumstances. Question 11. System analysis indicates that a facility is considering the integration of advanced smart grid technologies, including distributed energy resources, energy storage systems, and a comprehensive EOT-based building management system to enhance energy efficiency and operational resilience. What is the most professionally responsible approach to managing the inherent risks associated with this technological transition? Option A. Prioritize the immediate implementation of smart grid technologies based on projected cost savings and operational efficiencies, deferring detailed risk analysis to a later stage once the systems are operational. Option B. Focus exclusively on the technical performance metrics of the proposed technologies, assuming that vendors have already addressed all potential security and regulatory compliance issues. Option C. Implement energy storage solutions only after a thorough investigation into their long-term operational costs, without a concurrent assessment of their potential benefits for grid stabilization and demand charge management. Option D. Conduct a comprehensive risk assessment that identifies potential vulnerabilities, evaluates their impact on grid stability and data security, and develops mitigation strategies in alignment with relevant data privacy and critical infrastructure regulations. The correct answer is D. Conduct a comprehensive risk assessment that identifies potential vulnerabilities, evaluates their impact on grid stability and data security, and develops mitigation strategies in alignment with relevant data privacy and critical infrastructure regulations. Explanation. Scenario analysis. This scenario presents a professional challenge in evaluating the integration of emerging energy technologies within a specific regulatory context, requiring a nuanced understanding of risk assessment beyond simple cost-benefit analysis. The challenge lies in balancing the potential benefits of advanced technologies like smart grids and energy storage against their inherent risks, particularly concerning cybersecurity, data privacy, and grid stability, all within the framework of the Certified Energy Manager (CEM) exam's jurisdiction. A thorough risk assessment must consider not only technical feasibility, but also the regulatory compliance and ethical implications of deploying these systems. Correct approach analysis. The correct approach involves a comprehensive risk assessment that systematically identifies, analyzes, and evaluates potential risks associated with the implementation of smart grid technologies, energy storage, and EOT devices. This includes assessing vulnerabilities to cyber threats, ensuring data privacy compliance with relevant regulations, e.g., those governing data protection and critical infrastructure, and evaluating the impact on grid reliability and resilience. This approach aligns with best professional practice by prioritizing safety, security, and compliance, thereby safeguarding the organization and its stakeholders. It demonstrates a commitment to responsible innovation and adherence to the ethical principles expected of a certified energy manager, ensuring that technological advancements are implemented in a manner that is both effective and secure. Incorrect approaches analysis, focusing solely on the immediate cost savings and operational efficiencies of smart grid technologies without a commensurate assessment of cybersecurity risks, represents a significant regulatory and ethical failure. This oversight could lead to breaches of sensitive energy consumption data, violating data privacy regulations, and potentially exposing the organization to legal penalties and reputational damage. Similarly, prioritizing the rapid adoption of EOT devices for energy management without a robust plan for data security and system interoperability ignores potential risks of system malfunction, unauthorized access, and noncompliance with emerging standards for connected devices. This approach demonstrates a lack of due diligence and a failure to uphold the professional responsibility to implement technologies safely and securely. Another incorrect approach would be to dismiss energy storage solutions due to perceived complexity without a thorough risk-benefit analysis that considers their role in grid stability and potential for demand charge reduction, thereby missing opportunities for significant energy cost optimization and potentially failing to meet energy management objectives. This demonstrates a failure to critically evaluate all aspects of a technology's potential impact. Professional reasoning. Professionals should adopt a structured risk assessment framework that begins with defining the scope of the technology under consideration and its intended application. This should be followed by hazard identification, where potential risks, technical, operational, security, regulatory, are cataloged. Risk analysis then quantifies the likelihood and impact of these hazards. Risk evaluation determines the acceptability of these risks, often against predefined criteria. Finally, risk treatment involves developing strategies to mitigate, transfer, accept, or avoid identified risks. This systematic process ensures that decisions are informed, defensible, and aligned with regulatory requirements and ethical obligations. Question 12. Process analysis reveals that a building's HVAC system is underperforming, leading to high energy consumption and occupant complaints about inconsistent temperatures. The client is seeking immediate cost reductions. As a certified energy manager, CEM, you have identified several potential strategies, ranging from simple operational adjustments and minor repairs to significant equipment upgrades and building envelope improvements. The client is particularly interested in solutions that offer the quickest return on investment. Which approach best aligns with your professional responsibilities and ethical obligations as a CEM? Option A. Propose immediate implementation of the most advanced and energy-efficient HVAC technologies available, prioritizing cutting-edge solutions regardless of the initial capital investment or the building's specific operational needs. Option B. Prioritize only those immediate low-cost retrofits that can demonstrate a very short payback period, deferring any recommendations for more substantial system upgrades or building envelope improvements to a future date, even if these deferred measures offer significant long-term energy savings. Option C. Focus exclusively on addressing the occupant comfort complaints through immediate, but potentially superficial, adjustments to thermostat settings and air balancing, without a thorough investigation into the underlying system inefficiencies. Option D. Recommend a phased approach that begins with low-cost operational improvements and minor repairs, followed by a detailed plan for more significant upgrades and building envelope enhancements based on a comprehensive life cycle cost analysis and projected energy savings. The correct answer is D. Recommend a phased approach that begins with low-cost operational improvements and minor repairs, followed by a detailed plan for more significant upgrades and building envelope enhancements based on a comprehensive life cycle cost analysis and projected energy savings. Explanation. Scenario analysis. This scenario presents a professional challenge where a certified energy manager, CEM, is tasked with optimizing HVAC system performance. The challenge lies in balancing immediate cost savings with long-term energy efficiency and regulatory compliance. The pressure to demonstrate quick financial returns can conflict with the ethical obligation to recommend the most sustainable and effective solution, even if they require a larger initial investment. The CEM must navigate potential conflicts of interest and ensure that recommendations are based on sound engineering principles and adherence to relevant energy codes and standards. Correct approach analysis. The correct approach involves a comprehensive assessment of the HVAC system's performance, considering all relevant factors including operational efficiency, maintenance history, and the building envelope. This approach prioritizes a holistic view, aligning with the CEM's ethical duty to promote energy conservation and responsible resource management. It also ensures compliance with the spirit and letter of energy efficiency regulation, which often mandate performance standards and encourage lifecycle cost analysis. By recommending a phased approach that includes both immediate low-cost measures and a plan for more significant upgrades, the CEM demonstrates professional integrity and a commitment to achieving sustainable energy savings. This aligns with the CEM's role in advocating for best practices in energy management and correct approaches analysis, recommending only immediate, low-cost retrofits without a plan for addressing systemic issues in the HVAC system or building envelope is an ethical failure. This approach prioritizes short-term financial gains over long-term energy efficiency and sustainability, potentially leading to suboptimal performance and continued energy waste. It also fails to fully address the underlying causes of inefficiency and may not meet the performance expectations of energy codes or standards. Suggesting a complete system overhaul with the most advanced, expensive technologies without a thorough analysis of the building's specific needs and the cost-effectiveness of each component is also professionally unsound. This approach risks over-engineering and may not provide a justifiable return on investment, potentially violating the CEM's duty to act in the best interest of the client and to recommend practical, efficient solutions. It also fails to consider the potential for simpler, more cost-effective solutions, focusing solely on occupant comfort complaints without a systematic investigation into the root causes within the HVAC system and building envelope is an incomplete approach. While occupant comfort is important, addressing it without understanding the underlying energy performance issues misses the core mandate of an energy manager. This can lead to reactive, inefficient solutions that do not achieve optimal energy savings or address potential regulatory noncompliance related to system performance. Professional reasoning. Professionals in energy management should adopt a systematic, data-driven approach. This involves 1. Thoroughly understanding the client's objectives and constraints. 2. Conducting a comprehensive audit of the building's energy systems and envelope. 3. Analyzing operational data and identifying areas for improvement. 4. Evaluating potential solutions based on technical feasibility, cost-effectiveness, including lifecycle costs, and regulatory compliance. 5. Presenting a clear, prioritized plan with a justification for each recommendation, considering both short-term and long-term benefits. Ethical decision-making requires transparency, objectivity, and a commitment to promoting sustainable energy practices. Question 13. Which approach would be most effective for a certified energy manager to identify and prioritize interventions for improving the electrical system's efficiency and reliability in a large industrial facility, considering potential risks? Option A. Focus solely on replacing the oldest lighting fixtures with the most energy-efficient models available. Option B. Rely on vendor proposals for upgrades to switchgear and transformers based on their perceived benefits. Option C. Implement power factor correction measures immediately across all major motor loads to maximize immediate energy savings. Option D. Conduct a comprehensive risk assessment that evaluates the likelihood and impact of electrical system failures and inefficiencies, prioritizing interventions based on this analysis. The correct answer is D. Conduct a comprehensive risk assessment that evaluates the likelihood and impact of electrical system failures and inefficiencies, prioritizing interventions based on this analysis. Explanation. The scenario presents a common challenge for certified energy managers, identifying and mitigating risks associated with electrical system inefficiencies and potential failures in a facility. The professional challenge lies in prioritizing interventions that offer the greatest return on investment in terms of energy savings, operational reliability, and safety, while adhering to relevant standards and regulations. A thorough risk assessment is crucial to avoid costly reactive measures and ensure a proactive, data-driven approach to energy management. The correct approach involves a systematic risk assessment that prioritizes potential electrical system failures and inefficiencies based on their likelihood and impact. This aligns with best professional practices by ensuring that resources are allocated to address the most critical issues first. For a CEM, this means considering factors such as the age and condition of equipment, operational history, potential for downtime, safety hazards, and the financial implications of energy losses. Adherence to the principles of risk management is often implicitly or explicitly guided by professional standards and potentially referenced in CEM exam materials, dictates a structured evaluation process. This approach ensures that decisions are defensible, transparent, and focused on achieving optimal energy performance and system reliability. An incorrect approach would be to solely focus on the most visible or easily quantifiable energy losses without a comprehensive risk evaluation. For instance, prioritizing a power factor correction project solely because it offers a quick payback, without assessing the underlying health of the electrical distribution system or the potential for more significant, albeit less obvious, risks like harmonic distortion causing equipment failure would be professionally unsound. This neglects the broader risk landscape and could lead to misallocation of resources or overlooking critical safety concerns. Another incorrect approach would be to implement upgrades based on anecdotal evidence or vendor recommendations without independent verification or a thorough understanding of the facility's specific operational context and electrical load profiles. This can lead to suboptimal solutions, wasted investment, and potentially introduce new, unforeseen risks. Ethically, a CEM has a responsibility to provide objective, evidence-based recommendations, and failing to conduct a proper risk assessment violates this principle. The professional decision-making process for similar situations should begin with a clear understanding of the facility's operational goals and constraints. This is followed by a comprehensive data gathering phase, including energy audits, equipment surveys, and historical performance data. A structured risk assessment framework should then be applied to identify, analyze, and prioritize potential issues. This allows for the development of a prioritized action plan that balances energy savings, operational reliability, safety, and cost-effectiveness, ensuring that interventions are both impactful and sustainable. Question 14. The review process indicates that a certified energy manager, CEM, is tasked with evaluating the energy performance of a large commercial building to identify opportunities for significant energy savings. The CEM has access to several years of hourly energy consumption data, weather data, and operational schedules. Which of the following analytical approaches would best support the development of a robust energy conservation measure, ECM, proposal, demonstrating a commitment to data integrity and professional best practices? Option A. Rely on industry average energy intensity benchmarks for similar building types to identify potential savings without extensive site-specific data analysis. Option B. Conduct a detailed statistical analysis of the energy consumption data, correlating it with weather variables and operational changes to establish a statistically significant baseline and identify performance deviations. Option C. Focus the analysis on the most recent month of data to capture current operating conditions and identify immediate areas for intervention. Option D. Visually inspect graphs of the raw energy consumption data over time, looking for obvious peaks and troughs that might suggest areas for improvement. The correct answer is B. Conduct a detailed statistical analysis of the energy consumption data, correlating it with weather variables and operational changes to establish a statistically significant baseline and identify performance deviations. Explanation. The review process indicates a common challenge in energy management: interpreting complex data to inform strategic decisions. The scenario is professionally challenging because it requires the certified energy manager, CEM, to move beyond simple data collection and apply analytical techniques to identify actionable insights for energy efficiency improvements. The pressure to demonstrate ROI and justify investments necessitates a robust and defensible analytical approach, adhering strictly to the principles and best practices expected of a CEM. The correct approach represents best professional practice because it leverages established energy data analysis techniques and statistical methods to build a reliable baseline and identify significant deviations. This aligns with the CEM's responsibility to provide accurate and objective assessments. By focusing on statistical significance and correlation, the CEM can confidently attribute changes in energy consumption to specific factors, thereby supporting targeted interventions. This methodical approach ensures that recommendations are data-driven and have a higher probability of achieving desired energy savings, fulfilling the ethical obligation to clients and stakeholders for competent and diligent service. An incorrect approach that relies solely on visual inspection of raw data without statistical validation is professionally unacceptable. This fails to meet the standard of rigor expected of a CEM, as visual trends can be misleading and do not account for confounding variables or random fluctuations. It lacks the objective evidence required to support significant operational or capital expenditure recommendations, potentially leading to wasted resources and a loss of credibility. Another incorrect approach that prioritizes anecdotal evidence or industry averages over site-specific data analysis is also professionally deficient. This bypasses the core analytical responsibilities of a CEM, which include understanding the unique energy performance characteristics of a facility. Relying on generic benchmarks without a thorough understanding of the actual data can lead to inaccurate assessments and ineffective energy conservation measures, violating the duty of care. A third incorrect approach that focuses on a single, isolated data point or a short time window without considering historical trends or seasonal variations is similarly flawed. This demonstrates a lack of understanding of the dynamic nature of energy consumption and the importance of establishing a comprehensive baseline. Such an approach is prone to misinterpreting temporary anomalies as systemic issues or failing to identify long-term performance degradation, undermining the credibility of the analysis. The professional decision-making process for similar situations involves a structured approach. 1. Define the objective. Clearly understand what the energy data analysis aims to achieve, e.g., identify anomalies, establish a baseline, evaluate the impact of a measure. 2. Select appropriate tools and techniques. Choose analytical methods that are suitable for the type of data and the objective, ensuring they are statistically sound. 3. Establish a baseline. Develop a robust baseline of energy consumption using historical data and appropriate normalization techniques. 4. Analyze deviations. Investigate significant deviations from the baseline, employing statistical methods to determine their causes and significance. 5. Validate findings. Cross-reference analytical results with operational knowledge and other relevant data sources. 6. Communicate results clearly. Present findings and recommendations in a clear, concise, and data-supported manner, explaining the methodology and limitations. Question 15. The analysis reveals that a new commercial building project in a U.S. jurisdiction is being designed to achieve LEED Gold certification. However, preliminary energy modeling indicates that certain design elements, while meeting LEED energy performance prerequisites, may not fully align with the most recent International Energy Conservation Code, (IC), requirements for specific building envelope components. As a certified energy manager, CEM, what is the most appropriate risk mitigation and compliance strategy? Option A. Prioritize achieving LEED Gold certification by focusing solely on its energy performance prerequisites, assuming that LEED higher standards will inherently satisfy all IC mandates. Option B. Proceed with the design as planned to meet LEED Gold, and address any potential IC noncompliance issues during the building's operational phase through retro-commissioning. Option C. Disregard the IC for this project, as LEED Gold certification represents a superior level of energy efficiency and is the primary goal. Option D. Ensure the design strictly adheres to the latest IC requirements, and then identify additional measures to meet LEED Gold prerequisites and credits that exceed the IC baseline. Correct answer is D. Ensure the design strictly adheres to the latest IC requirements, and then identify additional measures to meet LEED Gold prerequisites and credits that exceed the IC baseline. Explanation. Scenario analysis. This scenario presents a common challenge for certified energy managers, CEM, where conflicting interpretations of energy efficiency requirements arise between a widely recognized voluntary standard and a mandatory building code. The professional challenge lies in navigating these discrepancies to ensure compliance, optimize energy performance, and avoid potential penalties or project delays, all while maintaining the integrity of the energy management system. The CEM must exercise sound judgment to determine which standard takes precedence or how to reconcile the differences effectively. Correct approach analysis. The correct approach prioritizes adherence to the mandatory building code, IC in this U.S. context, as the baseline for legal compliance. Building codes are legally enforceable minimum standards. While LEED certification offers significant benefits and encourages best practices beyond code minimums, it is a voluntary framework. A CEM's primary responsibility is to ensure the project meets all legal requirements. Therefore, the CEM should first ensure the design meets or exceeds the EIC requirements. Subsequently, CEM can then explore how to achieve LEED certification by incorporating additional measures that go beyond the EIC, leveraging the voluntary standard to enhance performance and achieve recognition. This approach ensures legal compliance while also striving for higher levels of energy efficiency. Incorrect approaches analysis. One incorrect approach is to solely rely on LEED certification requirements without verifying compliance with the EIC. This is a regulatory failure because LEED, being a voluntary standard, does not supersede legally mandated building codes. A project could be LEED certified but still be in violation of the EIC, leading to legal repercussions, fines, or the inability to obtain occupancy permits. Another incorrect approach is to assume that meeting the EIC automatically satisfies all LEED prerequisites or credits. While there is overlap, LEED often has more stringent or specific requirements for certain energy efficiency aspects than the EIC. Ignoring LEED-specific criteria and only focusing on the EIC would prevent the project from achieving LEED certification, thus missing out on the benefits associated with it and failing to fully optimize energy performance as envisioned by the voluntary standard. A third incorrect approach is to dismiss the EIC entirely in favor of LEED, believing that higher-tier voluntary certification inherently covers all legal obligations. This is a critical ethical and regulatory failure. The CEM has a professional obligation to ensure legal compliance, and the EIC is the established legal framework for building energy efficiency in the specified jurisdiction. Disregarding it is a dereliction of duty. Professional reasoning. Professionals in this situation should employ a hierarchical approach to compliance. First, identify and rigorously apply all mandatory codes and regulations applicable to the project's jurisdiction, e.g., EIC local amendments. Second, evaluate voluntary standards and certifications, e.g., LEED ISO 50001, to identify opportunities for exceeding minimum requirements and achieving higher performance. Third, develop strategies that integrate compliance with mandatory codes and the achievement of voluntary certification goals, recognizing that voluntary standards often build upon or go beyond code minimums. This systematic process ensures legal adherence, optimizes performance, and upholds professional responsibility. Question 16. When evaluating combined heat and power (CHP) system technologies for a U.S.-based industrial facility, which approach best aligns with the Certified Energy Manager (CEM) exam's regulatory framework and professional responsibilities? Option A. Prioritizing the technology with the lowest initial capital cost, assuming it will provide the most immediate financial return. Option B. Conducting a comprehensive analysis of the facility's thermal and electrical load profiles, evaluating multiple CHP technologies based on their lifecycle costs, operational efficiency, fuel flexibility, and compliance with U.S. environmental regulations, e.g., EPA standards. Option C. Choosing a system based on readily available vendor information without independent verification of performance claims or consideration of site-specific integration challenges. Option D. Selecting a technology known for its operational simplicity, even if it means a slightly lower overall energy efficiency and higher emissions compared to other options. The correct answer is A. Prioritizing the technology with the lowest initial capital cost, assuming it will provide the most immediate financial return. Explanation. This scenario is professionally challenging because selecting the most appropriate combined heat and power (CHP) technology requires a nuanced understanding of diverse operational needs, site-specific constraints, and the specific regulatory landscape governing energy efficiency and emissions within the United States, as per the Certified Energy Manager (CEM) exam's jurisdiction. A superficial assessment based solely on initial capital cost or perceived technological simplicity can lead to suboptimal performance, higher lifecycle costs, and non-compliance with environmental regulations. Careful judgment is required to balance economic viability, operational reliability, and environmental stewardship. The correct approach represents best professional practice because it prioritizes a comprehensive, data-driven evaluation aligned with the CEM's mandate to optimize energy performance and sustainability. This involves a detailed analysis of the facility's thermal and electrical load profiles, considering seasonal variations and future expansion plans. It also necessitates a thorough understanding of available CHP technologies, e.g., reciprocating engines, gas turbines, steam turbines, fuel cells, and their suitability for the specific application, factoring in fuel availability and cost, maintenance requirements, and integration with existing infrastructure. Crucially, this approach involves assessing compliance with relevant U.S. environmental regulations, such as those from the Environmental Protection Agency, EPA, concerning emission standards for NOx, SOx, and particulate matter, and potentially state-level, renewable energy, or clean air acts. The economic analysis should encompass not only capital and operating costs, but also the value of avoided energy purchases, potential revenue from selling excess electricity, and available incentives or tax credits, all within the U.S. context. An incorrect approach that focuses solely on the lowest initial capital expenditure is professionally unacceptable because it ignores the total cost of ownership and potential long-term operational inefficiencies. This can lead to higher energy bills, increased maintenance costs, and a longer payback period, failing to meet the economic objectives of the project and potentially violating fiduciary responsibilities to the client or organization. Another incorrect approach that prioritizes a technology with a simpler operational profile without considering its efficiency or emissions profile is ethically flawed. This oversight can result in higher fuel consumption, increased greenhouse gas emissions, and potential noncompliance with environmental regulations, thereby exposing the organization to fines and reputational damage. Such an approach neglects the CEM's ethical obligation to promote sustainable energy practices and minimize environmental impact. A third incorrect approach that overlooks the specific thermal and electrical load requirements of the facility, opting for a generic one-size-fits-all solution, is professionally unsound. This can lead to a system that is either undersized, failing to meet critical operational demands, or oversized, resulting in inefficient operation and wasted capital. This demonstrates a lack of due diligence and a failure to apply fundamental engineering principles to the specific application. The professional decision-making process for similar situations should involve a systematic, multifaceted approach. This begins with a thorough site assessment and load profiling. Next, a comparative analysis of suitable CHP technologies should be conducted, evaluating their technical performance, operational characteristics, and environmental impact. This analysis must be grounded in the specific regulatory framework of the United States, including federal and state environmental laws and energy policies. A robust economic evaluation, considering life cycle costs and benefits, should then be performed. Finally, a risk assessment, including operational reliability and regulatory compliance, should inform the final technology selection and system design. Question 17. Strategic planning requires a comprehensive approach to retro-commissioning a large commercial facility to improve energy efficiency. Given the facility's age and previous lack of systematic energy management, what is the most effective strategy to ensure the retro-commissioning process is thorough, verifiable, and contributes to long-term operational improvements, while adhering to best practices for energy management professionals? Option A. Rely on historical energy consumption data and general industry benchmarks to identify potential areas for improvement, without conducting specific functional testing on existing systems. Option B. Prioritize immediate cost-saving measures identified through a quick visual inspection and discussions with facility staff, implementing these changes rapidly to demonstrate quick wins. Option C. Focus on updating the building's control system software with the latest available patches and upgrades, assuming this will automatically optimize performance. Option D. Conduct a detailed review of all existing building system documentation. Develop a comprehensive functional testing plan based on design intent and operational needs, and meticulously document all findings, recommendations, and verification of implemented solutions in a final report. The correct answer is D. Conduct a detailed review of all existing building system documentation. Develop a comprehensive functional testing plan based on design intent and operational needs, and meticulously document all findings, recommendations, and verification of implemented solutions in a final report. Explanation. This scenario presents a common challenge in retro-commissioning, balancing the immediate need for operational improvements with the long-term integrity of the commissioning process and its documentation. The professional challenge lies in ensuring that the retro-commissioning effort not only addresses current performance gaps, but also establishes a robust foundation for future energy management and compliance. A key aspect is adhering to the established commissioning process, which is designed to systematically verify and document that building systems perform according to design intent and operational needs. The correct approach represents best professional practice because it prioritizes a thorough and systematic investigation, aligning with the core principles of commissioning as outlined in relevant industry standards and guidelines applicable to the CEM certification. This includes a detailed review of existing documentation, a comprehensive functional testing plan, and the generation of a detailed report that captures findings, recommendations, and verification of implemented solutions. This methodical approach ensures that the retro-commissioning is not merely a series of ad hoc fixes, but a structured process that enhances building performance, identifies root causes of inefficiencies, and provides a baseline for future monitoring and optimization. Adherence to these established processes is crucial for maintaining the credibility and effectiveness of energy management initiatives. An incorrect approach that bypasses thorough documentation and functional testing fails to meet the fundamental requirements of a commissioning process. This can lead to superficial fixes that do not address underlying issues, potentially resulting in recurring problems and wasted resources. Ethically, it represents a failure to provide a complete and accurate assessment, potentially misleading stakeholders about the true performance of the building systems. From a regulatory standpoint, depending on the specific jurisdiction and any associated energy codes or performance standards, such an incomplete process might not satisfy compliance requirements for energy efficiency verification. Another incorrect approach that focuses solely on immediate cost savings without a comprehensive verification plan risks implementing solutions that are not sustainable or that may have unintended negative consequences on system performance or occupant comfort. This deviates from the principle of holistic energy management, which considers the long-term impact of interventions. It also undermines the purpose of commissioning, which is to ensure systems operate as intended and efficiently over their lifespan. A third incorrect approach that relies on anecdotal evidence or assumptions rather than data-driven testing and analysis is fundamentally flawed. Commissioning is an engineering discipline that requires objective verification. Relying on assumptions can lead to misdiagnosis of problems and the implementation of ineffective or even detrimental solutions, violating professional standards of due diligence and accuracy. The professional decision-making process for similar situations should involve a clear understanding of the commissioning objectives, a commitment to following established protocols, and a focus on data-driven verification. Professionals must prioritize thoroughness, accuracy, and transparency in their reporting and recommendations. This involves 1. Clearly defining the scope and objectives of the retro-commissioning project. 2. Developing a detailed plan that includes documentation review, system assessment, and a comprehensive functional testing protocol. 3. Executing the plan diligently, collecting and analyzing data objectively. 4. Documenting all findings, recommendations, and verification results in a clear and comprehensive report. 5. Ensuring that implemented solutions are verified for effectiveness and sustainability. Question 18. During the evaluation of a large industrial steam system, a certified energy manager, CEM, identifies several areas of potential inefficiency and risk, including visible steam leaks, inconsistent steam trap performance, and aging boiler components. The plant manager is primarily concerned with maintaining uninterrupted steam production for critical manufacturing processes and is hesitant to approve any downtime for extensive system analysis or upgrades. Which approach best balances the need for operational continuity with the CEM's professional responsibilities for energy efficiency and risk management? Option A. Rely on the plant operator's experience and historical data to estimate the extent of inefficiencies and implement minor adjustments to steam pressure and temperature settings to mitigate perceived risks without further detailed analysis. Option B. Focus solely on addressing the visible steam leaks as they represent the most obvious energy loss, deferring any investigation into steam trap performance or boiler condition until production demands decrease. Option C. Immediately halt all steam production to conduct a comprehensive, system-wide diagnostic and upgrade project, regardless of the impact on manufacturing schedules, to ensure all potential risks are addressed simultaneously. Option D. Conduct a phased risk assessment, prioritizing the identification and mitigation of the most critical steam leaks and faulty steam traps that pose immediate safety or significant energy loss risks, while developing a long-term plan for boiler component assessment and potential upgrades during scheduled maintenance periods. The correct answer is D. Conduct a phased risk assessment, prioritizing the identification and mitigation of the most critical steam leaks and faulty steam traps that pose immediate safety or significant energy loss risks, while developing a long-term plan for boiler component assessment and potential upgrades during scheduled maintenance periods. Explanation: this scenario presents a professional challenge because it requires a certified energy manager, CEM, to balance immediate operational needs with long-term sustainability goals and regulatory compliance. The pressure to maintain steam production for critical processes can lead to overlooking potential risks associated with inefficient or outdated equipment. A thorough risk assessment is crucial to identify, evaluate, and mitigate these risks, ensuring both operational continuity and adherence to energy management standards. The correct approach, which involves a comprehensive risk assessment of the steam system, represents best professional practice. This aligns with the principles of energy management and the ethical responsibility of a CEM to promote efficient and safe energy utilization. By systematically identifying potential failure points, inefficiencies, and safety hazards within the steam generation, distribution, and condensate recovery systems, a CEM can prioritize mitigation strategies. This proactive approach not only prevents costly downtime and potential accidents, but also ensures compliance with relevant energy efficiency regulations and industry best practices, such as those promoted by the Association of Energy Engineers, for CEM certification. An incorrect approach that focuses solely on immediate production demands, without considering system integrity or efficiency, fails to uphold professional standards. This could lead to regulatory noncompliance if energy efficiency targets are missed or safety regulations are violated due to neglected maintenance or outdated technology. Ethically, it represents a failure to act in the best interest of the organization by not addressing systemic risks that could lead to significant financial losses or safety incidents. Another incorrect approach, which prioritizes the cheapest immediate solution without a thorough evaluation of its long-term impact on efficiency and reliability, is also professionally unsound. This can result in higher operational costs over time due to increased energy consumption and frequent repairs, potentially violating energy management principles and leading to noncompliance with performance standards. It demonstrates a lack of foresight and a failure to apply a holistic risk management perspective. A third incorrect approach, which involves implementing changes based on anecdotal evidence or without proper data collection and analysis, is professionally unacceptable. This can lead to misallocation of resources, ineffective solutions, and a failure to achieve desired energy savings or risk reduction. It undermines the scientific and data-driven foundation of energy management and can lead to regulatory scrutiny if performance claims cannot be substantiated. The professional decision-making process for similar situations should involve a structured risk assessment framework. This includes 1. Identifying potential hazards and inefficiencies within the steam system, e.g., steam leaks, faulty steam traps, boiler inefficiencies, condensate loss. 2. Analyzing the likelihood and impact of each identified risk. 3. Evaluating existing controls and mitigation measures. 4. Developing and prioritizing new mitigation strategies, considering cost-effectiveness, operational impact, and regulatory compliance. 5. Implementing and monitoring the effectiveness of chosen strategies. This systematic approach ensures that decisions are informed, defensible, and aligned with professional responsibilities. Question 19. The assessment process reveals that a commercial building's existing single-pane windows are a significant source of heat loss. The building owner is seeking a cost-effective retrofit to improve energy performance and meet current energy code requirements for the building envelope. Several options are being considered for the window upgrade. Which approach best balances energy performance, code compliance, and professional best practice for this scenario? Option A. Replacing only a portion of the single-pane windows with the most expensive, triple-pane windows with advanced coatings to achieve the highest possible R value, without a comprehensive assessment of the entire building envelope's needs. Option B. Installing storm windows over the existing single-pane windows to reduce air infiltration and provide a small improvement in thermal resistance. Option C. Replacing all single-pane windows with double-pane windows featuring low emissivity, low E coatings, and a U value that meets or exceeds the prescriptive requirements of the applicable energy code, while also ensuring proper air sealing around the new window frames. Option D. Prioritizing window replacement based solely on the lowest upfront material cost, selecting standard double-pane windows without considering specific U values or the need for low-E coatings. The correct answer is C. Replacing all single-pane windows with double-pane windows featuring low emissivity, low-E, coatings, and a U value that meets or exceeds the prescriptive requirements of the applicable energy code, while also ensuring proper air sealing around the new window frames. Explanation: the assessment process reveals a common challenge in building envelope retrofits, balancing cost-effectiveness with achieving optimal thermal performance and compliance with energy codes. Professionals must navigate various insulation types, window technologies, and air sealing strategies, each with its own R value, U value, and installation considerations. The challenge lies in selecting the most appropriate combination that meets or exceeds the applicable energy standards, without incurring prohibitive expenses or introducing new performance issues like thermal bridging. The correct approach represents best professional practice by prioritizing a holistic, integrated design strategy that considers the interplay between different building envelope components. This involves a thorough understanding of the specific energy code requirements, e.g., ASHRAE 90. 1. IC, or state-specific amendments if applicable to the CEM exam jurisdiction, and selecting materials and methods that demonstrably achieve the mandated performance levels. It emphasizes a systems approach, recognizing that effective air sealing, proper insulation installation to avoid gaps, and the selection of windows with appropriate U values are interdependent. This approach aligns with ethical obligations to provide energy-efficient solutions that benefit the client and contribute to broader energy conservation goals. Incorrect approaches fail to meet professional standards due to several regulatory and ethical shortcomings. Focusing solely on the lowest initial cost without considering long-term performance or code compliance is a significant ethical failure, potentially leading to suboptimal energy savings and non-compliance. Ignoring the impact of thermal bridging, for instance, by simply adding insulation without addressing structural penetrations, can negate the intended benefits and create pathways for heat loss, violating the principle of providing effective energy management solutions. Selecting window types based on aesthetic preference alone, without regard for their U values and contribution to the overall envelope performance, demonstrates a lack of due diligence and a failure to adhere to energy code mandates. Furthermore, neglecting proper air sealing techniques, which are critical for preventing uncontrolled air leakage and its associated energy penalties, represents a fundamental misunderstanding of building science and a failure to implement best practices. Professional decision-making in such situations requires a systematic evaluation of project goals, budget constraints, and regulatory requirements. A professional energy manager would first identify the applicable energy codes and standards. Then, they would assess the existing building envelope's performance, identify key areas for improvement, and research available technologies and materials. This will be followed by a comparative analysis of different retrofit strategies, considering their impact on R values, U values, air leakage, and thermal bridging, as well as their life cycle costs. The final recommendation would be based on a comprehensive understanding of these factors, ensuring that the chosen solution is technically sound, economically viable, and compliant with all relevant regulations. Question 20. Stakeholder feedback indicates a desire to improve motor system energy efficiency across the facility, with some suggesting immediate replacement of all older motors and others advocating for widespread installation of variable frequency drives, VFD. As a certified energy manager, which approach best aligns with professional best practices and regulatory expectations for motor system optimization? Option A. Conduct a detailed audit of existing motor systems to identify specific inefficiencies. Analyze load profiles to determine the suitability of VFDs for individual applications, and prioritize upgrades based on potential energy savings and return on investment. Option B. Install VFDs on all motors in the facility to maximize potential energy savings, regardless of their current operating conditions or the specific demands placed upon them. Option C. Immediately replace all motors older than 10 years with the latest high-efficiency models, irrespective of their current performance or load characteristics. Option D. Prioritize stakeholder suggestions for motor replacement and VFD installation based on the volume of feedback received, without conducting a technical assessment. The correct answer is A. Conduct a detailed audit of existing motor systems to identify specific inefficiencies, analyze load profiles to determine the suitability of VFDs for individual applications, and prioritize upgrades based on potential energy savings and return on investment. Explanation: this scenario is professionally challenging because it requires balancing competing stakeholder interests and technical considerations within the specific regulatory framework of the Certified Energy Manager (CEM) exam. The challenge lies in identifying the most effective and compliant approach to motor system optimization when faced with varied and potentially conflicting feedback. Careful judgment is required to prioritize actions that yield the greatest energy savings and operational benefits, while adhering to established industry standards and best practices relevant to CEM certification. The correct approach represents best professional practice because it prioritizes a systematic, data-driven evaluation of motor system performance. This aligns with the core principles of energy management, which emphasize understanding existing conditions before implementing solutions. By focusing on identifying underperforming motors and evaluating the suitability of variable frequency drives, VFD, based on load characteristics, this approach ensures that investments are targeted where they will have the most significant impact. This is consistent with CEM exam expectations, which value a thorough and analytical approach to energy efficiency projects. Furthermore, it implicitly adheres to NEMA and IEC standards by considering motor efficiency and operational suitability. An incorrect approach that focuses solely on replacing all older motors with the newest high-efficiency models, without a prior assessment of their actual operating conditions or load profiles, represents a significant regulatory and ethical failure. This approach is wasteful, potentially overinvesting in efficiency gains that may not be realized due to mismatched applications or incorrect sizing. It fails to demonstrate due diligence and a cost-effective strategy, which are fundamental ethical obligations for a CEM. Another incorrect approach that prioritizes the immediate installation of VFDs on all motors, regardless of whether the load profile justifies their use, is also professionally unacceptable. VFDs are not universally beneficial. Their effectiveness is highly dependent on the motor's load characteristics. Installing them unnecessarily leads to increased capital expenditure without commensurate energy savings, potentially even introducing inefficiencies in some low-load scenarios. This demonstrates a lack of technical understanding and a failure to apply best practices in motor control strategy selection, which would be a deficiency in a CEM's professional conduct. Finally, an approach that solely relies on anecdotal evidence from stakeholders without any technical validation or data collection is ethically flawed. While stakeholder feedback is valuable, it cannot be the sole basis for energy management decisions. A CEM has a professional responsibility to base recommendations on objective data and sound engineering principles, not just opinions. This failure to conduct proper analysis undermines the credibility of the energy management process and can lead to ineffective or counterproductive interventions. The professional decision-making process for similar situations should involve a structured approach. 1. Acknowledge and gather all stakeholder feedback. 2. Conduct a comprehensive audit of the existing motor systems, including motor type, age, efficiency ratings, load profiles, and operating hours. 3. Analyze the data to identify specific areas of inefficiency and potential for improvement. 4. Evaluate the suitability of various energy-saving technologies, such as high-efficiency motors and VFDs, based on the collected data and specific application requirements. 5. Prioritize interventions based on potential energy savings, return on investment, and operational impact. 6. Develop a clear, data-backed proposal for stakeholders, explaining the rationale behind the recommended actions. 7. Ensure all recommendations comply with relevant industry standards, e.g., NEMA, IEC, and regulatory guidelines.